Good morning.
Good morning.
Wow, last day of class. We've covered a lot of ground. So what I want to do today is wrap up our coverage of organic spectroscopy of chapter 10 in your textbook. And what I wanted to do is talk about carbon-13 NMR spectroscopy. And then spend a little time with an introduction to 2D NMR spectroscopy. We'll introduce two basic techniques that are widely used in what's called correlation spectroscopy, 2D NMR spectroscopy. One of these is COSY and one is HMQC. And we'll use these techniques in an example, and I'll give you a little bit of a feel of using them to elucidate structure. So C13 NMR is sort of an impossible technique. We already talked about proton NMR, and I said, well, there are really tiny energy differences involved. You've got a very small difference in Boltzmann distribution, and all of that is true, which gives you very low sensitivity, so you need very good instrumentation. All of that's true for carbon NMR spectroscopy, but it's even worse because most of the carbon in organic molecules, 98.9% of carbon is carbon-12, and carbon-12 is NMR inactive, meaning there's no way it doesn't have a signal. It doesn't have a nuclear spin. Carbon-13 has a nuclear spin, and its natural abundance is only 1.1%, which means if you've got a mole of methanol, only 0.011 moles of that methanol contain C13. So for all of these reasons, both the even lower Boltzmann distribution and a smaller dipole and the very low population of C13 NMR is less sensitive. You can often collect a proton NMR spectrum in, a minute or even less than a minute of data acquisition. Carbon NMR might take 30 minutes with more sample. But there's some factors that make it very valuable and also bring up the signal. So the peaks appear as singlets. In other words, you just get lines above the noise level. And this is due to a couple of reasons. In proton NMR, virtually all the hydrogens in the molecule are protons and spin-spin couple. In in C13 NMR, unless you have a very big molecule, there's going to be either 0 or 1 carbon-13 in a molecule. You're virtually never going to have a C13 next to another C13 or nearby to another C13, so you won't get spin-spin coupling. The C13 nuclei do couple with hydrogens, but all of the 1D NMR that you'll see for C13 NMR is run with what's called proton decoupling. What that means is that you are applying radio frequency radiation that's very rapidly flipping the spins of the attached protons, and as a result, the carbons aren't split by the protons, so you don't see the carbons appearing as doublets and triplets as quartets. All of that's good because it makes your signal bigger. A doublet is half as big as a singlet. A triplet is, well, the middle peak of a triplet is half as big, and the outer peaks are a quarter as big, and then it's smaller for quartets and so forth. So all of this concentrates your signal into a single peak, bringing it above the noise. Now, when I come to HMQC, we'll see how we're using the one-bond CH coupling, but you can just think of it as sort of magically decoupled, not coupling. Carbon-13 NMR has a tremendous spread of chemical shifts. Whenever I sketch out a proton NMR spectrum, I'll sort of sketch from 0 to 10, even though you can have peaks that are negative and you can have peaks beyond 10. When I sketch out a carbon-13 NMR, I'll probably sketch from 0 to 200, about 20 times as big, because there's about 20 times as much dispersion. Let me jot down some typical C13 chemical shifts. And a lot of it parallels what you've seen. So we've got this region of the spectrum, right? We run from about 0 to 200, and your aliphatics end up being on the left at low numbers, what we call upfield. And then your aromatics end up being more downfield. Next to an electron withdrawing group is more downfield. So an alkyl, typical alkyl is, say, about 10 to 40 ppm. Carbon next to a heteroatom, a halogen or an oxygen is maybe 50 to 80. Nitrogen doesn't have quite as big an effect. You might be more at the 40 range for an electron withdrawing group, but I'll give you 50 to 80 as sort of a round number. And all of these are rough numbers. I can easily show you examples that are outside. Alkenes and aromatics tend to show up at about the same place. In proton NMR, we said alkenes were sort of normally about 5 to 6, and aromatics normally about 7 to 8. In the case of C13 NMR, alkenes and aromatics end up at about 110 to 150. But again, I can easily show you examples that are at 100 ppm or examples that are 160 ppm. So those are sort of rough numbers. Acids, esters, the carbonyl groups end up being the most far downfield. The acid and ester carbonyl group ends up being at about 170. Ketones and aldehydes a little further downfield. Let's say about 180 to, again for the carbonyl, let's say about 180 to 210 is sort of a range here. Going to ask Stan and Sebastian to pass out a packet. I will be doing a good bit on the overhead today, and I have some handouts that I'll be displaying. Let's see. All right. So the first handout is really nothing more than all the numbers I've said and the little charts I've written. But when I look at a spectrum, typically I am reading the spectrum. In other words, I'm looking at the range of the spectrum and saying, oh, there's a peak over here. There's a carbonyl peak. It's probably an ester. Or there are some peaks over here. They're probably some alkene or aromatic. Or, well, of course, there's a bunch of alkyl stuff. Many molecules have it. Or, oh, there's a peak over here at 63 parts per million. I probably have a carbon attached to an oxygen atom. Same thing on the proton NMR. I'll look alkyl stuff. Oh yeah, I see a methyl triplet. I see a methyl doublet at about 0.9 parts per million. oh, I see some stuff from about 2 to 3 parts per million. That might be a singlet, say at 2.1 parts per million, 3 hydrogens. Maybe it's a methyl group next to a carbonyl, or maybe it's a methyl group off of a benzene ring. Sort of the midfield region, oh yeah, we have maybe a hydrogen near on a carbon connected to an oxygen, alkenes, aromatics, and the like. Yeah?
When you say, like, when you look at it, you basically read it off, is that kind of like with the reliability of, like, IR, where it's like 1700 carbonyl kind of thing?
So the question is, when you read a spectrum, is it the reliability of IR? And I would say yes, in the way that there are sometimes surprises in the IR. A carbonyl next to a double bond or a benzene might be at 1680. A carbonyl that's part of, say, a lactone ring might be, depending on the size of the ring, might be at 1775. And you'd still say, oh, it's a carbonyl, so it's not carved in stone. Oh, a carbonyl is 1700 or 1720. But yeah, if you read that way, it's pretty reliable. Now, I'll tell you in some problems that I give in a more advanced class, people sometimes get surprised. Like a carbon with 2 oxygens attached is at 100, usually about 100, 103 parts per million. So people might look and say, oh, I think it's an alkene or an aromatic, and yet they'll see, well, wait, there's only 1. And eventually they'll figure out, no, it's a carbon with a lot of electron withdrawing groups. I mean, I can show you examples of an alkene that is at 40 parts per million. So I can take things way out of there. But again, the sort of norm would be, yeah, certainly as you're getting introduced. I love to sort of teach from the rules and then the exceptions, and that's one way to think about it. So yeah, basically a starting point. It's a very good starting point. Other questions? All right, so that's one of the things that I like to do, and I urge you to do, is read. Now, there are lots of useful things you can get from C13 NMR. One quick thing is simply, well, let me give you an example of a spectrum, and I'll show you. I should show you what a spectrum sort of looks like. So here would be, say, a spectrum of propanol. We'll come back to propanol in just a moment. And so you have a peak, and it would be a singlet, a line at about 63.6. And then you'd have another line at about 25.8. These are actual numbers, of course. Another line at about 10.0. And so if I were reading this spectrum, if I were looking at this spectrum not knowing I had propanol, the first thing I'd be looking at here, and again, this is on the ppm range, I'd say, oh yeah, of course there's some aliphatic stuff, but then there's some carbon that's standing out, and I'd be thinking, oh yeah, maybe a carbon next to an oxygen or a heteroatom. So that's one thing you can do with C13 NMR. Another thing that's very valuable about C13 NMR is you can often pick up on symmetry. And so, for example, if you look at the molecule toluene, you would expect, even though toluene has 7 carbons, you wouldn't expect 7 resonances because the molecule has symmetry to it. In other words, the orthocarbons are identical. The metacarbons are identical. So you'd expect not 7, but 1, 2, 3, 4, 5 lines in the C13 NMR spectrum. There are other little clues when you're reading a C13 NMR spectrum. And again, I'm just going to sort of sketch it out. I could put up a spectrum. We'll get some real spectra in just a moment. But there are other little clues in the C13 NMR spectra. For example, so the NMR spectrum, the C13 NMR of toluene looks something like this. There's a line at 137 that's pretty small in height, a line at 129, and another line at 128 that are pretty tall, and then maybe a line at about 126 that's half as tall. And then over here, all the way down at 7, there's one more line. So that's sort of what you'd see. So your first idea might be there are 5 unique types of carbons, but there are also little hints. Quaternary carbons are often further downfield, but also quaternary carbons, due to a variety of reasons with not having hydrogens attached to them, end up being very small. So usually when I see a really short peak, it's like, oh, that's probably a quaternary carbon. In other words, that peak corresponds to this. Even though we don't use integration in C13 NMR because it's not very reliable, you can often get an idea from the heights of other peaks. Like I can be pretty darn sure that the 128 and 129 peaks, I don't know which corresponds to which, but I can be pretty sure that one of them corresponds to the ortho and one of them to the meta. And then the shorter one at 126, I can be pretty sure that it corresponds to the paraproton, the paracarbon. You'll notice the methyl group. Remember I said we're only talking rough numbers on ranges. You'll notice the methyl group here is at 7 parts per million. And again, that's no big surprise. You know, those numbers 10 to 40 are not carved in stone. But the main thing, if I were looking at this spectrum here, I'd say, oh, we've got 5 unique carbons. It looks like an aromatic compound, probably because, you know, if it were 2, I'd say maybe it's an alkene, maybe it's aromatic. With 4, I'd say probably an aromatic. But other clues will clue you in, like degrees of unsaturation and so forth. Coming back to symmetry, let's see how good you are at recognizing symmetry. This molecule is orthoxylene. How many lines would we expect in the NMRs, in the C13 NMR spectrum? 4 lines. The methyls, you've got a plane of symmetry here. So your methyls are symmetrical, your quats are symmetrical, your ortho, or whatever you want to call it, your meta, or whatever you want to call it, are symmetrical. Metaxylene, how many lines? Five. You've got symmetry in the molecule, so you've got your 2 methyls are symmetrical, your 1 carbon between them, the 2 carbons to which they're attached, these 2 carbons and this carbon. All right. Paraxylene. All right, we're gonna go with votes, right? So we're gonna go with votes here. Okay, 4 is gonna be, I don't know, we'll call it Bernie. How many people for 4? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 votes. All right, how many people for 3? We'll call it Donald. How many for 3? Nobody?
Oh, wait.
1, 2, 4, 5, 6, 7, 8, 9. 10, 11, 12, 13, 14 votes. All right, and I don't know, should I go 5 or 2? 2, we'll call it Hillary. All right, anyone for 2? All right, so yeah, so we've got two planes of symmetry. So the methyl groups are symmetrical, and then these guys are all symmetrical, and then we've got the quats. So basically, it is indeed Donald at 14 votes. All right. All right. All right, now I've got a really, really tough one. All right, so here's all right, so this is 3-methyl 2-butanol. So it's got a molecular formula of C5H12O, right? A saturated carbon compound with 5 carbons in it has a formula of 2n plus 2. Oxygens don't affect it, so 2n plus 2, 12 hydrogens. I can do that without even thinking, knowing there are no carbonyls or rings in the molecule. How many lines? 5. Give it to me. Why 5?
Oh, because those carbons would not be the same because of that stereocenter.
Hey, you got it. This is a stereocenter, even though I've drawn it in flatlands. And so the 2 methyls are diastereotopic. In other words, this molecule consists of enantiomers. Well, doesn't matter, but even if I had a pure enantiomer, even if I just had 1 enantiomer, I would have diastereotopic methyls. And so it's 5 lines in the NMR spectrum. I've asked that question to a room full of organic chemists, professors, and more than half of them got it wrong. So it's very easy to get fooled on stereochemistry. And just to demonstrate it as a point of fact in your handout packets, sure enough, I grabbed again from Aldrich the spectrum, and we see 1, 2, 3, 4, 5 lines in the C13 NMR spectrum. I should also point out to you that what looks like a triplet here from the methyl groups is actually 2 overlapping doublets. In other words, those methyl groups, you see them as diastereotopic in the proton NMR as well. They each give doublets, but if those doublets happen to be very near to each other, they look like a triplet. All right, so I want to talk at this point and then give us an example on 2D NMR spectroscopy. So 2D NMR spectroscopy is spectroscopy that uses, it's actually not the way you plot it, although you will see the plot look different. 2D NMR is a technique where you're running 2 frequency dimensions. That's not really important to you. But suffice it to say, it's not that you have a one-dimensional plot in one case and a two-dimensional plot in another. Anyway, there are a couple of main types of experiments, but I'm going to focus on what's called correlation experiments. And these experiments give connectivity, and this is very useful, connectivity, because they can help you tell what's connected to what. Connectivity, you get it already from coupling patterns. You see it when you see a triplet and a quartet, you say, oh, that's probably a methyl group next to a CH2 group, particularly if one is 3 hydrogens, if the triplet's 3 hydrogens, and the quartet is 2 hydrogens. COSY goes ahead and gives this by a specific what's called cross peak for hydrogen-hydrogen coupling. And that coupling can be any sort of coupling that gives rise to splitting. It can be 2-bond coupling, 3-bond coupling, long-range coupling. Any case where you would get splitting, you can get a cross peak in the COSY spectrum. Depending on the degree of splitting, your cross peak may be weaker or stronger. If the coupling constant is very small, you may not pick it up. The other technique is HMQC. HMQC is a heteronuclear technique. It gives CH coupling, so I'll write it as C13H coupling. In other words, it tells you it happens to be 1-bond coupling, but it tells you what hydrogens are connected to what carbons. So I'll say what H is, or let's say which H is connected to which C13. Well, let's just say which C, because in the end it doesn't matter. And in the case of proton coupling, we can say which peaks are coupled to each other. All right, so by way of a kind of a gentle introduction, I wanted to give you a couple of sketches and get used to the anatomy, and then we'll look at our real example and solve a simple structure. So this is a sketch, cartoon if you will, of the COSY spectrum of propanol. Propanol is just big enough for me to make my point. And the actual 2D spectrum, again in this cartoon, is this square over here. What I've shown along here on the top are my, again, cartoons of the 1D spectra, which one often puts on the axes to help look at it. Remember I said 2D NMR has actually 2 frequency domains. You have what's called an F2 or frequency 2 axis, usually plotted on the horizontal, and an F1 axis, usually plotted on the vertical. And those frequency axes, in the case of a COSY, are both the H1 frequencies. And then we've plotted the 1D spectra over the edge here. Now you know propanol. You should be able to assign your resonances from my cartoon. What I like to do is I like to letter my peaks. So if I see 4 sets of peaks in a proton NMR, I'll call them A, B, C, and D. And you probably are good enough with NMR that you could recognize, oh yeah, the CH2, that's a triplet, that's downfield close to 4 parts per million, 3.5 parts per million or so, that's going to be the CH2 group that's right next to the OH group. And you'd probably recognize, oh yeah, that triplet that looks like it's about 0.9 parts per million or thereabouts, that's probably Ph.D. And this sextet that's pushing 2 parts per million, that's a methylene group that's beta to an electron withdrawing group, that's C. And the OH, I said, well, OHs often don't couple. There's your singlet. Now, in the 2D NMR spectrum, I want to take us through the anatomy. So the 2D NMR spectrum in a COSY has what you call a diagonal. I'll write it up here. And the diagonal has peaks on it that basically correspond to the 1D spectrum. So you see a peak here, or that corresponds to A, corresponds to B, corresponds to C, and corresponds to D. Those aren't important. That's not going to give you any new information. The diagonal doesn't give you new information, but these guys here, symmetrically disposed about the diagonal, these are what are called cross peaks. And the cross peaks are what give you the new information. And it's kind of like, anyone play the game Battleship? Okay, you know, where you do a crisscross, right? So if I look at our A, B, C, D here, this cross peak is A to C. And that's telling us that our methylene is coupled to the other methylene. And the next cross peak, again sort of in the style of Battleship, is C cross D. And that's telling us that our methylene C is coupled to D. So there we go. That's basically reading our cross peaks and using that to get what we would otherwise only get from pattern recognition. All right, so that's a COSY. This is an This is an HMQC. HMQC is the heteronuclear experiment that gives our carbon-hydrogen couplings. On our F2 axis, we have the proton dimension. And now, on the F1 axis, we have our C13 dimension. What I like to do is I like to number my carbon resonances and letter my proton resonances. So I call my proton resonances A, B, C, D. I call my carbon resonances 1, 2, 3, 4. I like to number my resonances because I like to letter and number my resonances because I know resonances. I may not know what they correspond to, but I know, oh, there's a peak here, 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 there's a peak here. What we can then do is figure out how those resonances connect. So here's our molecule, and in this case, of course, we had already, for the point of demonstration, I had already gone ahead and assigned the proton resonances to the respective protons in the molecule. And so the way I like to annotate it is the OH is B. I have a CH2 group that's A, a CH2 group that's C, My pen's getting a little dull here. And a CH3 group, that's D. Now what we get from the cross peaks here, you notice there's no diagonal. And the only cross peaks are carbon-hydrogen correlations. In other words, what carbon is connected to what hydrogen. So carbon number 1 is connected to A. Carbon number 2 is connected to C. And carbon number 3 is connected to D. In other words, if I wanted to, I could write my designations right down here. C1H2A, C2H2C, C3H3D. It's my way of annotating things. Let's see if I have a sharper pen over here. All right, so with this basic introduction in hand, I want to turn us to an example. And the example is going to be to figure out the structure of a simple molecule. And that's next in your packet. And I'm going to give you a little information about this molecule. This is a molecule with a formula of C7H14O2. Now you should be able to tell from that formula that you have one ring or double bond, because if the molecule had no rings or no double bonds, it would be CnH2n plus 2. In other words, it would be H16. It's H14. So we say it has 1 degree of unsaturation. I look at the IR spectrum. I see a carbonyl. And the position of the carbonyl is interesting, 1743, which ketones are generally sort of 1715, 1705 to 1725, thereabouts. Esters are usually a little higher, about 1735 to 1750. So I'm suspecting an ester. I see a CH2 group, or at least I see some hydrogens on a carbon next to an oxygen. I see a peak at 171 parts per million, and all of that is pointing toward an ester. So I think I have an ester group. If I continue with my inspection of the spectrum, generally I'll measure, and it's hard over here, generally I'll stick a ruler or something on, or I like a grid on, and I can measure. I got about 1.7 or 1.8 for all of these guys here. In other words, it's probably about 1.8 per hydrogen. I got maybe 5.2 over here and maybe 10.6 over here. 10.6. So those are just the rise of the integral as measured with a ruler. 5.2. All of these are 1.8, I think, or 1.7. So I think it's about 1.8 per hydrogen. In other words, this ends up being 1 hydrogen, 1 hydrogen, 3 hydrogens, 1 hydrogen, 1 hydrogen, 1 hydrogen. That ends up being 6 hydrogens. And if you look closely, you can see this peak over here is a doublet and a triplet that overlap on each other. So I'm going to go ahead and I'm going to letter my peaks here. And we'll go A, B, C, D, E, F, G, and H for my proton peaks. Now, up until this point, with NMR, we've been relying on pattern recognition. That triplet that's next to or that CH3 that's next to a CH2, where we see the triplet and the quartet and the ratio of integrals. So there are certainly things that we can pick up from pattern recognition here. I've got a peak that's 6 hydrogens, except it looks like 2 peaks. It looks like I've got a doublet here and a triplet here. Well, it's probably methyl groups. One methyl group is probably next to a CH2 group to make it into a triplet. One methyl group is probably next to a CH group to make it into a doublet. I've got a group over here that's also 3 hydrogens, that's a singlet. That's probably a methyl group. It's probably not a methyl group that's on an oxygen. Might be a methyl group, say, next to a carbonyl. That would make sense, like an acetyl group. I've got this ABX pattern here. That probably is 2 diastereotopic methylene protons. They're at 3.9 parts per million, 3.93 and 3.86 parts per million. So they're probably next to an oxygen. We think it's an ester. So you could start to, and then the fact that it's an ABX pattern says they're splitting each other, and then they're split by one other coupling partner. So it's probably an OCH2CH. This is a problem that you could do without 2D NMR, just by fitting the pieces together, but it would take a little bit of cleverness. I want to make this into a little bit more of a science. Here's our C13 NMR. Don't worry about the depth spectra right now. We're not going to cover that. 1, 2, 3, 4, 5, 6, 7 unique resonances. All right. So I'm going to turn my attention next to the HMQC spectrum. And I want to correlate my peaks. So I want to connect my carbons and my hydrogens. So here are my carbons. We start at number 2. The carbonyl doesn't have any hydrogens connected. 2, 3, 4, 5, 6, 7. Here are our protons. A, B, C, D, E, F, G, H. I get very, very particular about continuing to label things. Now we'll get our connectivities from our cross peaks. So we get 2 connects with A, and 2 connects with B. I usually like to go ahead and write my letters over, my numbers over my letters on top. We get 5 connects with C over here. I walk along the spectrum. We get 3 connects with D over here. Now, we thought we had a stereocenter. We see 2 hydrogens, diastereotopic hydrogens, connected to carbon 2. And we also see that we've got 2 diastereotopic hydrogens connected to carbon number 4. So in other words, 4 gives us 4E and 4F. Gets a little crowded over here. I can kind of see that 6 lines up with G and 7 lines up with H. There's an expansion here to help you out if you're having trouble seeing it. In other words, that doublet that looks like it's G, this line and this line, that doublet over here show up as 6G, and that triplet shows up as 7H. Now, I got to tell you, I got this from a book called Silverstein. They did cheat a little bit. This cross peak actually should extend out to here. I think they doctored their spectrum. I've seen them do it in a couple of other cases. So it should come right under the triplet. But you can see which lines up. The 6G lines up here, the 7H lines up there. All right, so we've completed our assignments here. And now I'm going to turn to the COSY, and we're going to build up the whole molecule. Now, the COSY spectrum here, due to space, they didn't plot it. They didn't plot the proton on the other axis, which is OK. We can just cross things here because we know how they cross. So I'm going to transcribe my labels 2A, 2B, 5C, 3D, 4E, 4F, 6G for the doublet, and 7H for the triplet. I'm going to mark my diagonal. Oops. Just get that out of consideration. If I had it, I'd probably use a ruler. So we get a little cross peak here. We see that our 2B, that's 2B over here, and that's 2A. We see that our 2B and 2A cross with each other. Well, that's not really providing us any new information. We know we're trying to build up the framework of the molecule. We know that those two high diastereotopic hydrogens, A and B, are attached to carbon 2 and that they're going to couple to each other. So that's not really useful. And remember, carbon 2 is the one that is downfield in the C13 NMR, and it's the one with the methylene group that we think is connected to the oxygen. And we believe that the oxygen is part of an ester, and that ester has carbonyl number 1 to it. All right, let us now build up the rest of the molecule. So we see a cross peak here, right? This is 3D, this is 4E, so we see 3D crossing with 4E, and this is 4F, we see 3D crossing with 4F. So that starts to be useful because now we're saying that our CH, whoops, what did I do? Oh, I missed one cross peak here. Okay, so we've got 2 more cross peaks I want to dispatch with up here. Those are interesting. 2A cross 3D, and 2B cross 3D. Okay, so that's starting to build. In other words, we're coming out from here. 3D is crossing with 2A and 2B, right? They're crossing over there. So that is starting to build up our connectivity, C3HD. And the next set of cross peaks that I've already marked continues to build up our connectivity. It says that C3HD is connected to C4HE and HF. In other words, without having to interpret patterns, our cross peaks are basically walking us through the construction of the chain here. It's a little hard to see on the expansion, but if you look, you kind of see that this cross peak here is lining up with the 6G. Not all the way. These two are lining up with the 7H. This one's a little narrower, a little bit higher in number. So that cross peak over there is going to be 3D with 6G. And that's useful because it says now that I go ahead, I have a valence here, I can attach my C6H H3G methyl group. Let's finish up. We've got a couple of cross peaks here. This cross peak doesn't really tell us anything new. It's 4E with 4F. That's just a diastereotopic methylene crossing with itself. The last two cross peaks here, that's 4E with 7H. And this one is 4F with 7H. That completes our chain. C7H3H builds out our chain. We still have one carbon we haven't placed. Number 5, carbon 5 that's attached to HE. There are 3 HEs. It's a methyl group. Remember, that's the one that's at 2.1 parts per million. Methyl group, 2.1 parts per million. On a benzene ring, probably, except we don't have a benzene ring. On a double bond, probably, except we don't have a double bond. Or on a carbonyl group. In other words, we finish our construction, C5H3E. There is our molecule. There is our ester. There is our C7H14O2 molecule. And that is how I like to use 2D NMR spectroscopy plus reading IR, reading your proton, reading your carbon to solve the structures, to determine the structures of organic molecules. Well, thank you very much for your time and for your attention. It's been a pleasure being with you.